Okay, so welcome to our 2 p.m. session, which is on the latest in quantum algorithms, part 1. And our first speaker is Abid. So the floor is yours.
Cool, thanks. Hi, my name is Abid. I'm a research scientist at JP Morgan. I think the last thing you would have expected is to see spin-boson systems to be associated with this fine thing, but here we are. The thing I'm going to talk about today is on QAOA, and in particular, simulating QAOA pretty efficiently using spin-boson systems. So I'll just give a quick refresher on QAOA. Consists of P layers of the same kind of circuit type, one in which you evolve a cost Hamiltonian that you're trying to optimize, followed by a mixing operator, which is just going to be most likely just 1 to Rx rotations on single qubits. And you apply this many, many times, and the idea that as you apply more layers, the closer you get to the ground state of your system. And what we're interested in is understanding the algorithmic performance of QAOA as it scales with, say, system size, or maybe how close you get to the ground state. To preface, there is some promising evidence of QAOA having good algorithmic scaling, and in particular to compare with classical heuristics that exist today. So one way is to do this kind of comparison is look at how you take some model that you're interested in optimizing, and you run QAOA on it and compare it to classical heuristics as you increase the system size. And that's what's being shown on these 2 tables here, where we're looking at how the time to solution as a function of system size, and comparing that to doing a fitting on that, and then comparing that to the best classical algorithms. And these 2 works have shown that there is evidence that for these problems, QAOA has a better performance with system size than their respective classical heuristics. Another thing we can do is look at how close our solution gets, time to solution as a function of how close we are to that ground state. And so that's what this talk is about. In particular, how well we can approximate ground states of the Sheraton-Kirkpatrick model, which I'll describe later, using QAOA.
Can I ask just those scaling laws?
Yeah.
How much trust should we have? I mean, I suppose that they are fitted on very small system sizes, actually. Like small P's, and you see 1460 there, but
yeah. So I don't know exactly the particular system sizes that are referenced here, but I think they're on the order of tens to hundreds of qubits, I think. And there are additional these aren't not all these algorithms are running QAOA. They're more like simulating QAOA via other means. Yeah, I'll explain how that is kind of done in this talk. But yeah, I think to get the actual numbers, we could go to the archive. Another nice thing about QAOA is that there's no variational parameter optimization, as opposed to say like VQE, where generally when we're running QAOA, we're kind of given some fixed schedule that's independent of the instance that we're working on, and we can easily extrapolate from, say, we have classical heuristics to extrapolate from some low QAOA depth to a higher QAOA depth. And any optimization that we would want to do, we can do such a thing classically. So I'll talk about this model that we're actually trying to work with, and which is the SK model. This is a well-studied spin glass model that's NP hard in the worst case. It's over a complete graph, all-to-all connectivity with couplings that are weighted by sampling from a normal distribution. Now, oftentimes we're not going to talk about the worst case. In this talk, we're going to talk about the average case, which is what multiple classical algorithms also work with. And these classical algorithms achieve this 1 minus E approximation in a time that's kind of linear in system size and inversely scaling with with that epsilon error. Here you can think of it as like fidelity with a ground state. Or in this case, maybe the distance from your actual energy, your ground state energy. So the unproven folklore belief suggests that the best classical heuristics is something like n over epsilon squared, and we'll see how we can do better with QAOA. We have evidence showing that QAOA can perform better. In this talk or in this work, we're going to study the performance of QAOA in the infinite size limit. We'll talk later about why this is something that's desirable. So we can, because of this linear scaling, we can just divide that cost function over n and just look at the dependence on the time to solution as a function of this epsilon, this error, approximation error. Right, and then another nice thing about this feature is that the SKB model has a known result in the infinite size limit. This is called and in the average case, and it's called the Parisi value. It's what won Giorgio Parisi a Nobel Prize. Did you have a question?
I guess that was the question. I mean, this has a polynomial solution, right? This problem, even for a single instance with the Montanari algorithm.
Yeah.
And you're claiming a speed up over that algorithm.
So that is, are you talking about AMP?
Yeah.
Yeah, so this is still unclear at the moment because that AMP we don't have that comparison yet. That's something we're currently working on and verifying that to be the case. Here we're not comparing it with AMP. We're just going to give you the actual scaling result. So yeah, the goal is to numerically evaluate this quantity, the energy as a function of your QAOA depth P, where you're fitting in some gamma beta parameters. So to understand how to actually compute or how we are computing this in this work, I'm going to give some background on how it was previously computed by a group at Google, where they do this iterative approach recursively of finding these values. And the way that they do this is by taking, looking at these like ZZ individual ZZ terms and doing some clever tricks with it. Right, so we'll take like a p=2 example and just expand out what a component of this cost function looks like when we do this expansion. And then we can insert identity in between each of these operators to turn all these things into scalars, and you're going to have a sum, exponential sum of exponential number of terms of these scalars. But then you'll take all the components that contribute to the phase, put them all together, take all the terms that look like mixers or that are mixer terms, put them together, and you're going to get something that looks like this, where you have a component that's solely in terms of the operator, like the cost Hamiltonian, and one that's solely in terms of the mixer. And then to obtain higher P, this is done by recursively updating what we'll call this Hermitian matrix G. It's P+1 plus P, is P+1 dimensional. And the elements of these of this matrix is very similar to what this P=2 example is, except now when you like put in the SK parameters or this SK cost function, instead of C here, you have elements of your G matrix from a previous iteration. And so you do this P times, and to get the actual QAOA energy, to get the actual QAOA energy, you just take this bottom row, and those components are used for the energy. So in that work, their goal was to compute these elements of this G matrix, and because of the exponential number of terms in that sum, the prior work was only able to get to p=20, because it scales exponential in p. Now we'll get to the technical results of this work, which is that if you stare hard enough at these elements of G, they look like overlaps between two spin-boson systems. Now it's very not obvious why that would be the case, but a argument or something that you can kind of argue is that when you take two coherent states and you give overlaps between them, they're exponentials of their amplitudes. And so something like that is happening here. The overall technical results are more in the supplement of this paper, of this work. But for now, we'll just take that as is. And then the QAOA energy that we obtain is just obtained by taking overlaps between these spin boson systems. So now the revised goal of this work is to now just simulate these spin boson systems, compute overlaps, and then we're done. Okay, now I'm gonna get a little bit into understanding what these spin boson systems are and how they're computed. So these states that are elements of that G matrix have a form where you have a single qubit coupled to p bosonic modes. And the way that these states are simulated or evolved is where we iteratively apply a QAOA-like layer. That's not QAOA, but it's similar to it. And you know these as M. They consist of a spin rotation that's applied solely on the spin qubit. And then we apply multi-mode displacement operators on the bosonic parts. And so that's what these states are. Maybe some more information on how this is related to this G matrix is that these multi-mode displacements is like your gamma values times this L matrix, where L is done by a decomposition of this G matrix. And so if you were to like take an overlap between two states like this, you're gonna have something that's like L dagger times L, and that's gonna contribute to this component. And then these exponentials of spin rotations is gonna contribute to your spin, your RX components of your QAOA circuit. Okay, and so it turns out that we could simulate this. Well, we can simulate this with MPS, of course, but it turns out that it's not hard to simulate with MPS, which is a very surprising thing. So that's what I'm going to show here in this bottom plot, where we're going to denote each spin boson mode as having a site in the MPS, and then we're also going to have a spin 1/2 site assigned to it too. So what does it look like when we're actually applying this one of these M layers onto our MPS? It's better to think of my MPS as two MPSs, one consisting of like a spin 0 mode and one consisting of spin 1 part. So I'm kind of taking that spin boson part where it's just one spin in p bosons and just doing two spins or two MPS of p bosons.
The blue and the brown are disconnected, right? They cross. They don't talk.
So these two talk.
They don't talk. Okay.
So this thing will conform the MPS itself. So think of like this. These sites are the MPS. Yeah. So well, yeah. It's you think of this as like a non-normal MPS, but what the gates that you're applying will, because if I were to think about these as like two MPSs, I can like put them together and have this extra wire determining whether I'm on MPS 0 or MPS 1, corresponding to spin 0 or spin 1. So applying the multimode displacement operator is very easy. You're just applying it. You're applying single gates on each of these spin boson modes. That is given here. It's bottom right. These are displacement operators that you're applying onto the MPS sites, followed by RX rotations on the spin qubits. So what this RX rotation is really, if you have two separate MPSs, you're just adding and subtracting them together to form two other MPSs. So right, this is a very simple contraction that you can do. And then this does not blow up your bond dimension. The thing that actually does blow up your bond dimension is when you're doing this RX gate, which is essentially taking two MPSs and adding them together. I'll sweep through this, but essentially a way to do this is by doing a bunch of contractions and SVDs to kind of bring that RX gate all the way to the end to form your new MPS, and that's your layer. And then a little thing to actually get these G matrices is that these elements of these G matrix is that you just like apply a Z gate onto the spin component, and that's how you get your QAOA energy. And the interesting or the cool part is that we don't need a high bond dimension to represent these states accurately. And so this is proof of that. What I'm showing is bond dimension versus QAOA depth. This is a log-log plot. I'm also showing the running time versus QAOA depth, also on a log-log plot. And you can see that it scales pretty mildly for relevant precision values. And as a reminder, prior work we had it scaled exponentially in P. So we did this using Perlmutter's machines. It's pretty great to run these. And now doing this, we can now evaluate QAOA energies of the SK model in the infinite size limit in this average case for very large P. And so the highest P that we've actually evaluated, but not optimized, is P is equal to 120. What we did was we did optimize parameters up to P is equal to P is equal to 80, and then extrapolated parameters to P is equal to 120. And so this thing on the y-axis is just the energy error between what the pre-C value and what we're getting from QAOA. And doing some fitting, we see that this epsilon is almost 1.13. So that is the time to solution to get an energy or at that level there. Great. One more thing I want to show is that what's cool is that we can use these parameters that we found in the infinite size case, and we can apply them to finite size numerics. And so here we're actually just doing state vector simulations for finite size instances, like 2,000 instances. We run QAOA, and we have the same exact. We have a similar scaling error. The approximation at finite sizes match infinite size prediction. So I'll stop here and just give some summaries and questions.